Let's go on to the second one. We're going to use a calculator to evaluate each radical. I don't think we really need to use a calculator, but we will as instructed. What I find helpful as I go through the radical unit is if I have this in my brain or written down on a piece of paper that I can easily generate and refer to. So the blue are the list of perfect squares, 2 times 2, 3 times 3, 4 times 4. And the red is the list of perfect cubes, 2 times 2 times 2 times 3. 27 is 3 times 3 times 3, et cetera, et cetera. Now, perfect powers of 4 as well, they're listed there. 2 times 2 times 2 times 2 is 16. 3 times 3 times 3 times 3. Anyways, you get the point. These numbers are really important to sort of have in your mind or on a piece of paper that you can easily refer to because they simplify radicals that much easier if you're able to refer to these. So, anyways, we have a calculator, don't worry. The square root of 121, yeah, that's 11, right? 11 times 11. If you notice, 121 was on the perfect square list. The cube root of 64, I believe that is 4. Right? The fourth root of 81 is 3. So far, so good. Now, what we have here, now I should have a calculator, and I apologize, but you have a calculator. The square root of 90, I'm just going to peg it, I don't know, maybe 9.4 or something of the sort. It's not really that important. What we're here is to see things when things work and when things don't work. Now, the cube root of 50. Well, let me just go over here. So cube root of 50. So the cube root of 27 is 3. The cube root of 64 is 4. So I know that it's between 3 and 4. So I'm just going to put approximately 3.5. Now, the square root of negative 38. If I do that, you'll get an error in your calculator. And simply because it does not exist, not in the real number plane anyways. So the reason for that is because the square root is essentially which two numbers multiply to that radicand. And that radicand is negative 38. There's no two numbers that multiply to a negative. So the square root of negative 38 does not exist. And we can maybe even say this further. Now, you may recall from last year 2 important conclusions. If the index, now I'll just make sure that we all know what we're talking about. If the index of the root is even, that's that number there, then the radicand must be, so there's the radicand must be positive. However, if you notice in E, if the index is odd, well then your radicand can either be positive or negative. Because an even number of negative numbers multiplied together will yield a positive result, but an odd number of negative numbers multiplied together will yield an odd result. So that's where that comes from. Anyways, simplifying, if a radicand represents a real number or expression and has an even index, the radicand must be non-negative. And that's fairly important. So basically, be careful when your index is even, the radicand must be positive. So we're going to use inequalities to identify the values of the variable for which the radical represents a real number. So here, all we need to ensure is that that radicand, x, is greater than 0. And in fact, I just wrote a simple inequality that my radicand, x, is greater than or equal to 0. In B, again, I have my radicand has to be greater than, my radicand has to be greater than 0, greater than or equal to 0. So I can put it in terms of x. So right now I have 5, or x plus 5 is greater than or equal to 0. So, but if you subtract 5 to both sides, you'll get x is greater than or equal to negative 5. So those are the values where our radicand, where the value of our radical will yield a real number. So similarly here for C, my radicand, and I take it first step algebraically, I put my radicand as greater than or equal to 0. However, I'm going to choose to work a little bit algebraically so I could isolate x. Now, an inequality works very similar to an equality or an equal sign. So if I add 6 to both sides, that equality sign is still maintained. Like, it still points the same way. And if I divide both sides by 2, that equality still remains. So here, this radical will have a real value provided that x is greater than or equal to 3. Now, let me go to D. D is kind of a tricky one. Now, if you notice, the first thing I did was I'm interested when my radical is greater than or equal to 0. It just happens that my radical is 4 minus x is greater than or equal to 0. One way around this here, or one way to work with this, is simply to add x to both sides. And we get 4 is greater than or equal to x. Now, typically, we like to write our variable on the left. And so if I write it, the variable on the left, if I say 4 is greater than or equal to x, is logically equivalent to saying x is less than or equal to 4. From this stage, if you typically we read it left to right, but if you read it right to left, it is x less than or equal to 4. So that's one way of doing it. Another way is I could take this inequality and I could multiply both sides by -1. And why would I do that? Well, if you notice, my x is negative here. So maybe before, I could do that now, but maybe I have the idea, you know what, I'm going to subtract 4 from both sides. So since I subtracted 4 both sides, my inequality sign remains. However, perhaps now I'm like, I would really like to get rid of that negative sign. And the way that I can get rid of the negative sign is multiply both sides by -1. However, when you multiply both sides by -1, both sides of the inequality, the symbol changes direction.